Let us now look into a Python-based demonstration to understand cross-validation and hyperparameter tuning. So I'll be leveraging the same example which we have been looking for model evaluation. So under model evaluation, this example refers to the classification models where we have leveraged the HR analytics dataset. So instead of starting fresh, since we already have everything in place, we have the data ingested into memory, we have the function created to encode categorical variables, we have created the concatenated dataset with all the categorical variables transformed into one hot encoded format, and then finally we also have the train and test data split. So let's put that into memory once again, and that's it. I think we're good. Now let's start fresh once again. Let's say since logistic regression model is already created, we'll start simple. Let's say model is equal to logistic regression, and we have a fresh new model in place. Now instead of directly using the function fit, we'll pass x and y over here, and then later test that using x test and y test. We can actually create a cross-validation data set. In this process, let's say we choose k-fold cross-validation, where we can set the value of k as 10. So essentially, it creates 10 equal partitions of the data set. It will use 9 for training, the 10th one for testing, and will repeat this process 10 times, wherein each partition is used for testing once. Now, there's a handy function where I can do this very easily. So we'll say from sklearn dot model selection, we'll import k-fold, and we'll also import another function which will come in handy later on. It's called cross-val score. We've loaded into memory these two functions, and we have instantiated model. Now how k-fold works is, let's create a k-fold object. We'll say cv is equal to k-fold, and we'll pass the value of n splits as 10. Now once this is executed, this can be executed to run the split function, which will return the indices for 9 partitions and 10 partitions separate. Now how do we do it? So we'll say for train index and test index in cv.split. Here we would pass the x dataset, x, which is our training data set. Now this will return in 10 iterations 9 partitions into the train index and 1 partition into the test index. The number is 10 because we have chosen n splits as 10. Had we chosen plus 5 or something else, this would have been a different scenario. Now for each of these iterations, what we would do is we'll say model.fit. Now we'll pass the train dataset over here and then score it separately in the test dataset. So let's say we'll use first model fit and we'll say x.ilog. Now I'm using ilogs because I have to subset a partition of the data set using the train index. Now the train index goes over here, and I would say y.ilog. Now since y has probably more columns, I'll just say I'll take the last column, which will be the first I'll say train index, and then I just want the last column just to be on the safer side. Now let's just run this part to see if everything is working fine. Yes, it executed without an error. Now to understand how this works is, now this is the for loop which will iterate through each iteration within cv split. This will run 10 times and return 9 partitions stored into train index, 1 partition stored into test index, and these will be simple indices. I'm leveraging these indices to actually create a training data set out of the actual data set for the logistic regression model. So presume that in X, which is our data set, we have approximately 1000 rows. So in this process, 900 of them will be randomly selected into train, the remaining 100 will be selected into test. And I'm using this 900, which is a subset of the main one, to train our data set, and then we can use the remaining to actually test our data set. Now let's just say we can print the values of the score. We'll say model.score. We'll first pass the values as it is, that is for this train data set, which is the 9 partitions combined together. So we pass the value into score, and then we print for the test data set. So over here, instead of train index, I'll say test index. So what it is essentially doing, we are creating 9 partitions, using 9 of them to train, 1 of them to test, and then we're also checking the score on the trained data set. Here we can check whether there's overfitting or underfitting, or is there huge differences between the scores on seen and unseen data. Let's just try to run this. Uh, let's say, okay. So you can see over here, like it's pretty much consistent. We have values between 78 and 80. So if you look over here, the first iteration is the score for the training data set, and the second one is the score for the test data set, and so on. And this is repeated 10 times. So we have 20 new records over here, and it's pretty much consistent. We have barely any difference. It's between 78% to 80 or 81% at the max. That's it. So it seems like when you do a simple cross validation, you can see that across 10 different iterations, the scores do not vary a lot. You can see relatively a stable model. So we can say the variance of this model is pretty low. So we have low variance achieved. So that's cross validation. Now another simple way would be you can directly use a cross val score, and over here we'll first pass x. So we'll first pass a model, which is model, and x comma y, and over here we'll just, let's say we'll take left, and we'll say CV is equal to 10. And now if we try executing this, here we have, so instead of using the function over here where we go manually and extract all of these indices, we can just leverage this function. And like now over here we can see the scores aren't really bad. It's pretty much consistent from 78 to 80. It's in sync with what we saw earlier also. So we can conclude that the model is relatively stable and has low variance. So that's cross validation. Now you can play around with this. Let's say you can increase the number of splits, you can decrease the number of splits. You can try different types of cross validation. sklearn does offer you a variety of different cross validation techniques. For the moment, let's park this topic over here and let's move on to another important topic which we covered recently, and that is hyperparameter tuning. So hyperparameter tuning. Now we have learned about 2 different techniques. The first one is grid search, and the second one is randomized search optimization. Now, as you already know, in grid search, what you would do is you would actually create a grid. So let's say you have a hyperparameter, let's say like C. C defines the complexity of regularization, and it can give a value which is a positive finite number. Now, it could be a value like 0.1 or 0.001, or it could be as high as 100. Generally, the moment you have a higher number, it kind of overfits. The moment you have a lower number, it kind of underfits. So what value would be the best one? Now, the ideal scenario would be you have a couple of values in your mind, you execute iterations on each of these possible values, and then select the best one. So rather than going manually and like executing this separately in 10 iterations, we have grid search function available within Python, which will help you automate this. So let's import the grid search function from sklearn. So we'll say from sklearn dot model selection, we import grid search. Now, how do we before dealing with grid search, let's create a dictionary of parameters. So how can we leverage this? We first create a model that we would like to execute. So in this case, logistic regression model. This is what we will use. So along with this, we pass the parameter space. Now, what we would do over here is, let's first define the parameters we want. So we'll say parameters is equal to, we'll create a dictionary and we've passed just one parameter, that is C in capital. And then define what kind of values we want to pass for C. So let's say we want to try with C is equal to 0.001, then we'll say 0.01, then 0.1, then 1, or let's say we'll take 0.5 also, 0.5, then we can have 1, then we'll have, let's say, 5, 10, and even 100. So these are a set of values that I would like to try with, and my agenda would be to take up the best value of complexity and then put it into my logistic regression model. Now, rather than trying them all of them iteratively one by one, I can use a grid search CV. So what I would do is I'll create a CV model, let's say, which is the grid search model. And I'll say grid search CV. I'll pass in the estimator and the parameter grid. Now I have a couple of additional parameters that I can kind of override, but then for now we'll just stick to the basic two parameters. So I'll pass model and I'll pass parameters, right? There you go. So we have a grid search object instantiated, and this is instantiated with a logistic regression model that has to execute n number of times, taking into account different values for this specific hyperparameter. Now, if you have, let's say, if you want to add in a couple of more hyperparameters, you can definitely do that. So in this scenario, we just considered one of them. Let's say you want to add penalty. We've not discussed much about penalty, so let's say we can add penalty as another element in the dictionary. So we'll say penalty, and penalty is defined as L1 or L2, so L1 or L2, and then we can complete the dictionary and execute it. But for now, let's keep it simple. We just have one simple hyperparameter. Now we have the model instantiated in the CV model. Now the rest of the story remains the same. What we do is we'll say simply CV underscore model, and we'll call it fit function. When we say fit, we'll pass x, and let's say we pass y as y left of y. So left is the target variable. Now if I execute this, CV model is now a fitted version of grid search. It has technically executed a logistic regression model for each of these values of the hyperparameter. Now, how do we know which is the best one? Let's just say CV underscore model, and we press dot. So it will open up the kind of attributes it has. So we have best estimator, best index, best parameters, best score, and so on. Now you can just select best estimator, and I can say enter. Now this is the best estimator that it had found in those iterations. Over here you can see it is defined C as 5, which means that out of all of these values, the best values were associated when C was 5. So to check it further, let's say instead of best estimator, you can say best score. There you go. You have the different scores over here. And you can have a couple of additional parameters. You'll see the cross validation results and many more. Now, this is how actually you can go ahead and create. So had you used more parameters, all of them would have changed over here. You can actually just go over here and say best parameters, and you get the values for the best parameter. Like since we have just used one hyperparameter, you can see one of them. Had you used penalty also, the best value for penalty would have popped up over here. So that's grid search. So instead of iterating through all of them, you can actually go ahead and create a grid which will define the list of possible scenarios it needs to consider for C. Now, if you have taken a closer look, there is one serious trade-off over here. So for example, we definitely have taken the best one out of this using grid search. But what is the possible trade-off? Now, this is the best possible value for this specific model will only come up if we have actually passed in the best value over here. But it's only going to choose one of these. It can't really go beyond this list. Now, that's the trade-off. If you have accidentally missed out thinking about what could be the best value, and then you gave some lame values over here, that's really going to not give you the best results. So to accommodate this trade-off and improve version, and another version would be, let's say another version would be like a brute force model. You can actually give an n number of arrays and then keep iterating in a laborious way. That's also not really ideal. So more optimized version would be randomized search cross validation. Over here, what happens is you actually, instead of defining the grid, you define a distribution. Now using this distribution, it actually goes in a fashion where it takes up one random value, finds what is the associated results with that specific value, and then takes a shot at finding the next best value. Now, since it has access to a wider range, since it's a distribution, the chances that you will achieve higher accuracy with a randomized search is kind of very high. Now, let's see, we have got from this model, we have got approximately 79.3% accuracy. there's a very high chance that we might get fairly or probably a marginally improved results with randomized optimization. Now, it's not necessary, but then there are chances. Now, since we might have missed out getting the best value over here, but in case if let's say the actual best possible outcome for the hyperparameter C, if it's located within this, then grid search will definitely give you better values than randomized search. So let's go ahead and use randomized search. So I'll say from sklearn along with grid search CV, I'll import randomized search CV2. Now I've executed it, it's in memory. Now similarly, instead of this parameters, I'll create a parameter list. Parameters, let's say I'll just give this name as 2. And instead of actually passing the grid, we'll actually pass a distribution. Now we can do this by importing from scipy.stats, we import uniform. Yes. Now this will help us create the uniform distribution, and let's say we create C as the uniform distribution with a scale of 4. Just execute this, and we can say parameters over here. C is the variable C which we have just defined over here as a distribution. Now if you use this over here, instead of this grid, it's actually going to take up the distribution which we have defined over here. Now let's try the same with the random search model. So we'll say CV underscore random is equal to random search model. Okay, and over here we'll pass first the estimator, that is model, then pass the parameter distributions. So we'll say param distributions is equal to parameters underscore 2. So that will suffice for now. Fair enough. Let's say CV underscore random dot fit, and we say x comma y of fit. Sorry, left. I got confused over here. And there we go. So we have the model fitted into this. And let's check CV underscore random dot best estimate. Now if you see over here, the best estimate it found was around C is equal to 1.98. And if you check CV underscore random dot best score, it is 79.34, which is not really great compared to the previous one, like 79.35. But so this is an exception. Like this is not a like so generally you would observe that when you use randomized search CV, you kind of tend to get better results than. Let's just try this once again. Probably because of the randomized function, we might get a better score. Okay, it's kind of the same. So that's fine. But then in a general practice, if you observe, we tend to get kind of better results when we use randomized search for hyperparameter tuning. But this was an exception. All right. So wrapping up, what did we learn today? We learned about cross-validation. We looked into hyperparameter tuning. We explored the two different techniques we learned previously in hyperparameter tuning. That is, first one is grid search, and second one is randomized search. That's it for now. We'll move on to the next topic, which is the last topic in this module, and that is ensemble modeling.